Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. Ladies and gentlemen, welcome back to another live stream. Alrighty, well, we're going to wait for 5 minutes until people join in. Okay, I'm gonna share the link here. Continuing our project. Let's go. Alright, announcements. Stream. Okay. Yep, cool. Pop out church. Let's go. All right. Great. All right, how much time have passed? 3 minutes. Okay, I'm just going to wait for the 5 minute mark or the 10-minute mark, and we're gonna start the stream. Just waiting. If anyone is interested, they can join in. Alrighty. Cool. Cool. Okay, I think we have reached the 5 minutes mark, so I'm pretty much going to start at this point. Okay, alrighty, well, okay, let's go. So I pretty much published the link yesterday to the new repo, of course after the prayer. Where is it? Codotaku. Right. I give it a really descriptive name. Really creative name, Vulkan Zig Compute, as simple as that. Okay. So here's the link if anyone have missed it. I also posted it in the last live stream in the comment section. And yeah, I just added some couple of things. So for example, I added the readme right there. Let me see the other stuff. Hold on a second. 5 commits, okay. Here I updated the readme. Well, let's actually start from scratch. Okay, so this is the first stream stuff that we had. Pretty much, I just added the git ignore with zcache and zig out there. You know, the submodule stuff for git, and yeah, the other cool stuff there. And I believe I also found that I'm using some struct name instead of self, which I fixed. And I don't remember really, but I think just some minor fixes like that. Or tweaks, should I say. And then there is, of course, the readme, the license. Readme and the license. The license is basically just MIT license. Alright, I added the readme markdown. Okay, Vulkan Zig Compute. Vulkan application is being written using the Zig programming language during live streams. The goals is basically learning the Vulkan API and limiting our scope to compute. Learning the Zig programming language, exploring the possibilities of Zig plus Vulkan compute. Okay. And then, of course, the build instructions, which is very simple. Just the Zig build run and you're done. Or Zig build run dash the optimizer release fast or release small. And then the license stuff, the contributions are very welcome. Feel free to submit pull requests, open questions and topics in the issues section. I just shamelessly copied some of these paragraphs from another repo, from other repos. So yeah, unless you explicitly state otherwise, any contribution intentionally submitted for inclusion in the work by you shall be licensed as above, without any additional terms or conditions. And we're going to try to follow the Zig standard library style, if possible. So there you go. Alright, and there is work. I just fixed this typo, autocomplete. And yeah, there you go. I added self here instead of q. I just made it self. And that's pretty much, I think, the stuff that I changed there. Then I updated the readme to add this performance cross-platform tiny size as much as comfortably possible. I again tweaked the readme to add minimum dependencies. And finally, I don't know what I added. Yeah, I just added that guy right there, okay, for formatting reasons. So that's pretty much it. All that got changed pretty much in there. And yeah, that's pretty much it for the repo right now. So I think let's go ahead and start the real thing right now. Okay, cool stuff. Well. So last time we have left it in that we have actually got the queues from the device and basically initted the device, which gave us the queues, and then we extracted the device from one of the queues pretty much, and then of course defer device.dinit. So yeah, that's pretty much it. Now I think we're going to go with compute stuff, and for that compute pipeline. And for that we have to start by actually compiling a shader. So, well, let's see how that's being done using the binding, because I remember there is a build thing for it. So okay, okay, it's here somewhere. Shader compiling. Let's look for shader. There you go, shader compilation. And you basically just say okay, and basically you just say const shader comp equal vacate gen shader compile step dot create, and you do this. So let's add this guy after in the build file. Where's the build file? Okay, build. There you go. Okay. Now I believe maybe somewhere around here. And builder, well, is basically B in this case. Although honestly I'd like to maybe rename this symbol to builder, why not, I guess. There you go. And you basically tell it the command that you want to use, which is in this case glslc -- target -env equal Vulkan 1.2. Here you basically say which Vulkan version you're using. In my case I'm using just 1.0 until now at least. And of course, to be able to use glslc command, you have to make sure that you have installed the what can I say, the Vulkan SDK. And hello Ibrahim, welcome to the live stream. So yeah, that's pretty much it, hopefully. So git package shaders shader comp dot add package shader comp dot get package shaders, and then shader comp dot add shader, and then here give it the path to the shader. Okay, cool. And then also you have some options right there. Let's have a look into the options real quick that are possible. There is additional arguments that should be passed to the shader compiler. There is watched files, paths of additional files that should be watched for changes to trigger recompilation, and to ensure that if compilation option changes, the shader is recompiled properly. Okay, cool. Alright, pretty much it. That's very much it. And there's a cache directory there. Okay, so right now I need to basically create a folder for shaders, I believe. So where we're gonna do that, well, I think we probably have to put it in src though, so we are able to get it, I guess. Maybe not actually. Let's try to do it anyway. So new folder, and here's shaders, and I'm just gonna put a very minimal shader right here just so we can see if it works. So minimal.comp, basically comp is the extension for compute shader. Okay, and supported GLSL version. So here you say, I believe, if I remember, you say version something. Well, let us go to my previous project. I have a little minimal shader right there. It doesn't really do anything, but it's just to make sure everything works. So Vulkan Zig, I believe. Let's go. And where is it? dev/shaders simple.comp. There you go. This is pretty much it. You say the version. In this case, let's try 450. then you give it the main function. And GLSL is basically kind of similar to C, to the C language. You could, in fact, with Vulkan use any language you want as long as it can compile to SPIR-V bytecode. So yeah. So for example, you could use GLSL, there's HLSL, and there's also some other crazy languages that you could find in the wild. But yeah, anyways, there's even, I believe, WebGL, something that I worked with when I was working with, I think, WGBU, right? But anyway, now how we can access our shader. Oh, first of all, I need to specify the path, which is going to be basically shader/minimal.comp. Okay, cool. And then you basically call it something. Well, I guess let's call it minimal shader. Alright, cool stuff. Now what we have to do next, let's see, Vulkan Zig. So Vulkan Zig provides functionality to help compile shaders to SPIR-V using GLSLC. It can be used from build.zig as follows. Upon compilation, GLSLC is then invoked to compile each shader, and the result is placed within Zig cache. All shaders which are compiled using a particular shader compile step are imported in a single file using embed file, and this file can be added to an executable as a package using get package. Okay, using get package. So we're using get package right here, as you can see, and we're adding package to the exe. Nice. And I guess you call the package whatever you want here, basically. To slightly improve compile time, shader compilation is cached. As long as the shader source and its compile command stay the same, the shader is not recompiled. So basically, we don't have to worry about recompile the shaders every time. Everything will be automatic for us, which is nice. The SPIR-V code for any particular shader is aligned to that of a 32-bit integer as follows, as required by vk create shader module. Amazing, perfect. So we say pubconst the name, then align of u32 embed file path. Cool. So let's try to actually import that guy. I think we have to probably import that shader stuff. So let's see how we can do that. Okay, let me make sure right now everything is working fine before we do any changes. And of course not. So let's see why that's the case. So expected 3 arguments found 2. 3 arguments. Good afternoon, Travis. Welcome to the live stream. Welcome back. Alright, so builder, we have the builder, and we have the compile command, and we have the output flag. So that is what's missing. I think they didn't update the readme, so they really have to update the readme for their documentation. It's very frustrating. But anyways, I think it's probably not something very major that got changed. So builder is fine. Then you have the compiled command, which is also fine. But then you have something called the output flag. So create a shader compile step. Create a shader compile step for builder. When this step is invoked by the build system, compile command shader source output flag path is invoked for each shader output flag. For example, one call this with create bglslc and then see the add shader. Where's add shader? Hello, Clousy. Welcome to the live stream. So see the add shader. vertex.glsl. The command will be glslc vertex.glsl -o. So I think we just have to add the -o flag. That's what's changed. So let's try that out, I guess. Hopefully that's the only change needed. So let's go and see. Zig build run. And no field or member function named add package in build.step.compile. I mean, come on. Okay, we have to waste another 1 hour to just get the build system working for us. That's crazy stuff. Okay. Well, that's what you get for adopting new technology. You have to figure everything yourself. So no field or member function named add package in vel.step.compile. But I do remember there is a comment here called, hold on a second, where is it? Here. Okay, so oh my god. Okay, so there's c.add shader. Then you tell it vertex.glcells. I mean, let's see if we can find some example maybe. Hold on a second. Let's see if we can find some examples here. So there is shaders here, but I don't think there is in the build system. Should be similar changes as above, exe.add module or exe.create module. Oh, well, let's try that out. Add module and create module. Where we should use create module? Let's try add module first of all. Sig build run. Error member function expected 2 arguments, found 1 in exe add module. So it is expecting a compile thing. Is exe a compile thing? Yeah, it seems like, I guess. Maybe. And then it needs the name. The name and the module. Add a module to be used with import and exposing it to the current packages module table using name. Okay, gotcha. So create module, he said. Well, I think basically the name would be shaders, just like they had there, and then maybe afterwards, is shader comp a module? No, it's not, I guess. So you say exe.create module, is that the case? That doesn't seem like it. Maybe shader comp. Well, I don't know. Let's see shader comp. Add a shader to be compiled. SRC is a shader source path relative to the project root. Returns the full path where the compiled binary will be stored upon successful compilation. Okay, let's try this hopefully, although I don't think it would work though. So maybe we have to say b.create builder.create module. Yeah, let's see. You give it some options there. Create module options. Well, so to make this work, well, where is this have just gone? Okay, add module. Where's create mod? There you go. Create module options. So you have a source file and then dependencies, module dependency. What? Source files and mod. I don't think this is the case, isn't it? Well. Source. Oh man, come on. Well, where did you get the example you're following? From the bindings page, from the binding readme, and it didn't work. It doesn't seem like it's it seems like it's outdated already. Oh man. So create module. Hold on. Where is the shader stuff? There you go, shader compilation. So I think this worked so far, but this kind of thing didn't. Do we have to maybe use add anonymous module instead? Maybe. Hold on. Add anonymous module and then maybe the name. Shaders. Let's see create, but this is also create module options. And you have to give it a source file and some dependencies. Some source file and some dependencies. Where's the source file in this case? This gives us a shader compile step. And this is what it contains. Weird. Alright, well. There is a get module function here. Hold on a second. What? Where this is? Yeah, so there's a shader compile step. Inside of it, I think there is another function called get module. Maybe that's what we need there. Hold on a second. Build.zig. Alright, well. Build.zig. And maybe I don't even need this stuff. Maybe. So I think you basically get the module, I guess. So maybe const, well, what's going on here? Const module is equal shader comp. Okay, so there's a lot of cool stuff here. So there's this get module here. Okay, so here we got a module. Great. Now how do we add that module into the exe? That's there. Alright, let's go. Shaders. And then I guess you add the module here. Hopefully that's the case. So also let me make sure to put this guy around here. And yeah, hopefully this would work. Let's see. I mean, at least it compiles now. So that's nice. So I basically have said, well, we could just get the module directly, honestly. Seems like you're on the right track. Yeah, that seems like it. Hey, nice. Yeah. So, well, glad I won't have to waste another hour like the last live stream just fighting with the build system and outdated documentation. Well, anyways. So this seems to compile. Now the moment of truth, let's try to use this up. Const shaders is equal to import, and I think you'd basically use the same name as you have told it here. I think that's probably the case. We won't get compile autocomplete, but it doesn't really matter for shaders. And also, so we have called the shader minimal shader, so I think we have to use this name right here to grab the shader. So let's try this out. Well, first of all, well, honestly, let's just go ahead and see. Okay, so std.debug.print. Let's go. And let's say shaders.minimal shader. Maybe. Oh, let's try it out. Any. And yeah, it works. It's, I guess, at least. It seems like it's given me some bytes. So that's a good thing. Let's try to maybe print the type of that guy. Type name. Let's see what it's going to give us. What are you drinking? Coffee. Coffee, coffee. Alright, expected type found U8. Alright, I wanted to know the type, but it actually failed, but at least mission have failed successfully because at least I got the type here because of the error. So oh man, 264. So it's a slice of U8s. Yeah, so we have basically, we're successful in doing that. Amazing stuff. Lovely. So now we could go to the next step, which is creating a shader module. So that's very nice. So let's create a shader module. Yo, embedded boy, welcome to the live stream. All right, so const shader module, okay, is equal to a struct. Let's go. Const self is equal to this. Well, this. Let's go. Fn init the fuel of every programmer. Fn init, okay. Well, self. Of course, this could error, and then fn dinit. I should probably try to create some kind of what can I say? Some kind of, I even forgot the name, but basically some shortcut of, it would basically create a skeleton for me like this. I don't remember the name of it, but basically, for example, in main you could say main, and there you go, this guy right here. When you press it, you get that guy. So yeah, something similar. I don't remember what is it called, but yeah, if anyone knows, we could maybe dig it up and find out how. It would probably speed up our development, so we don't have to create this boilerplate every time. All right, so the init function, let's see. Well, in the device wrapper, we need another device dispatch, yeah, device wrapper. We need another function called, I guess, create shader module, I believe. Maybe. And then, of course, destroy shader module. I believe, but let's, of course, make sure that's the case. Create shader module. Yeah, vk create shader module. Okay, so this is the stuff. So it needs device create info allocator shader module, just as, you know, typical Vulkan thing. Okay, cool. So let's go back there. Making init dinit, it's planned for ZLS. Oh yeah, that would be nice. So basically, you'd for example, you'd maybe say like class, and then you just enter, and it would just generate this whole skeleton for you. But of course, you could basically just rename it here, and you're done. You got the skeleton done, which would be cool. All right. So the init function would be, well, it needs the device, of course. So the device and allocation callbacks, vk.allocation callbacks. Okay. Now we would say device.vkd. Okay, nice. And honestly, since we have those function pointers in their own kind of space, namespace, which is the device in this case, I think vkd, vki, and stuff like that is kind of pointless. Maybe just calling it vk or something. But anyway, create module now. Create shader module. And then you give it the device, of course, the handle of this device in our case. And then we're going to give it the create info, which is going to be like this, the allocator. So of course, allocation callbacks. Let me know if you'd like me to try to kind of create some kind of debug allocation callbacks, so you can see like the Vulkan memory usage stuff. But anyway, create shader module. Well, so this would, of course, could error. So I'm just gonna say try, and that's basically the shader module. All right, well, so now what's the create info? Let's have a look. So flags. So we only have to give it the, I always forgot that YouTube eats links. Eats links. I don't know really I probably have something for that here, but you could always just send it in Discord, you know. Discord. Zig tools issues. Oh, I see. So yeah, you could always put it in Discord and I'll have a look. But anyway, search for create init d and its function. Sure. I think I have to add zig, right? Maybe ZLS then. Maybe I have to use this instead. ZLS issues. $689. How do you actually find that guy? Nope, I couldn't find it. But anyway, you could put the link for me right there. Well, yeah, I sent you a link in Discord anyway. That's fine. Code actions and autofix. The issue contains a collection of possible code actions. Yeah, exactly. That can be integrated into ZLS. Some of them may not be easily implementable. Without that and that, feel free to make suggestions. In use parameter, remove parameter, discard parameter. Nice. I think init, there you go. Create init d init function. Nice. Nice. So I think you basically give the name, like the fields, and then it kind of like generates for you some boilerplate. Nice. Cool. All right. Amazing stuff. Amazing stuff. So let's go back into action. So code size, right? Code. Is it code size or what exactly? Hold on a second. Code size and p code. Okay, code size, let's go, is equal to what? Well, we're going to of course get the bytes, so maybe it's going to be const. I'm not sure. Does it really have to be? I don't think so. Anyway, let's just say u8, and that's going to be basically the data or the code basically. So it's going to be a slice, and then here I could say code.len, and here .code, sorry, .pcode, I believe, right? Oh man, yep, pcode is equal to code.ptr, but of course I have to make sure to cast it to the right pointer, I believe. But let me just try this out anyway. And of course, at the end of the day, we have to have a handle here. So handle is vk.shader module. Let's go. And then what's other than that? Well, you return this guy. Then you say dot handle is equal to this guy. All right. So I guess I don't need this maybe. Well, anyway, what's happening there? Okay, cool. That seems to work out, I guess. All right, so that's the handle, I guess. Well, let's try to use it. But of course, here in dinit, you would get self. and it would say self dot device. Well, I need to store the device in the allocation callbacks, of course. So, well, device and allocation callbacks. Well, in fact, I probably need this guy right here. Let's go. Just gonna copy this. Let's go. And then self dot, let's see, dot device, I guess. Dot vkd dot destroy module. And then we're going to give it the device and the handle of the device, of course. And the shader module is going to be self.handle, and the allocation callbacks self.allocation callbacks. Alright, so just a second, I'm gonna be back. I'm just gonna do something real quick. Alright, back. Alright, Mike. Cool. So self.device.vkd destroy shader module. Yeah. Destroy shader module. Okay. So now let's try to create a shader module. Here you give it the device, and here you give it the code, which is going to be shaders.minimal shader, I guess. And then here well, null for now. And of course, try it out. So, and then we're going to say defer shader module.dinit, and let's go. No field named code size, instruct vk shader module create info. What? Code size. I believe maybe because they got changed or what? I think so. P code, maybe something like this. Is that correct? Yes, that's correct, I guess. So array literal will require address of operator to coerce a slice type. Sure, let's do that. So we have to coerce it to a slice. All right, cast discards const qualifier. So should we have like a const here, I guess? Okay, cool. Now we basically have to make sure to turn this pointer into this guy. So let's do that. ptr cast, I believe. Oh, okay, hold on a second. There's also a line cast, but no, let's just go with, actually we have done that before in the project. Hold on a second. Yeah, here it is. Okay, let's see, src main. Let's look for shader module. Let's go. All right, so this is how we have done it. ptr cast and align cast. But maybe we only need ptr cast in this case, since I think the binding maybe is doing the alignment for us, if I remember. So here we would say, where you have gone? Okay, there you go. So you just say cconst u32, just like this. Copy ptr cast code.ptr. But of course you add the C there, and yeah, hopefully that's the case. Let's try this out. Oh yeah, we have to actually use line cast. So there's no okay, let's go ahead and do it. Go.ptr. So here the alignment comp time, which is going to be 4, and then the pointer is going to be that guy, code.ptr, and hopefully that's basically the case. And the misinstruct field device, oh yeah, so I forgot about device here. So dot device equal device as always, and dot allocation callbacks is equal to allocation callbacks, and there you go. Yep, nice. All right, so where we should go now? Oh yeah, I want the vk config. So let's go to another bash. Let's grab vk config, and let's switch to, instead of validation, let's go with API dump, and let's zig build run. Best to not use any kind of C pointer types in your zig. If you can avoid it, zig pointer types are just safer. Are you talking about this one? Oh, it seems like it works, right? Nice. All right, so let's make sure that this is correct. Okay, so as you can see, vk create shader module is being called. Nice, nice, nice. The size is correct, the shader data stuff, and yeah, pretty cool. Working all good. So we have just created the shader module now. Nice. All right, well, is there any questions so far? So that's pretty much it for the shader module. Now we have to work, I think, with the compute stuff, okay? So with the pipelines, sorry. So, or honestly, let's just go with the pipeline layout, I think, because it's pretty simple. Yep, almost any zig PTR type will coerce into a C PTR type. Nice, that's nice, that's very nice. Yeah, let's just go, I think, with pipeline layout because it's pretty simple, pretty standard stuff. And maybe it's pretty much kind of similar to shader module. It's just kind of boilerplate code, basically, kind of. So anyway, const shader module, instead of shader module, we're going to go with the pipeline layout. Cool. So here vk dot pipeline layout, and what's other than that? There's no code anymore, just the device and the allocation callbacks, and then handle. Instead of create shader module, it's probably going to be create pipeline layout. Let's go. And of course, the info would change. I probably won't give it anything for now, although later on this would be useful in actually binding the, or should I say, the layout of the pipelines. So we could basically bind resources into shaders so they can work on them. But for now, we're fine. We're just going to keep it like that, empty. Cool. So destroy also pipeline layout. And of course, we're going to add those functions so they could be loaded. Dot create a pipeline layout is equal to true. And dot destroy pipeline layout is equal to true. Cool. Cool. I think maybe this is all that we need, maybe. Destroy pipeline layout, self.handle, and self. Yeah, I think that's pretty much it for pipeline layout. So let's see. Const pipeline layout is equal to try pipeline layout dot init. You give it the device, of course. The allocation callbacks is null for now, and yeah, and defer pipeline layout dot dinit, right? And let's try this up. Misinstruct fields, pset layouts. So this takes pipeline create stuff. And yeah, this seems it doesn't have a default for some reason. Pset layouts. For now, I just like to make it as null. I don't know why they don't have it as a default of null, but anyway, let's just do it ourselves then, I guess. So we cannot actually give it null there. I think a slice maybe, something like this possibly. Pset layouts. Let me make sure one thing real quick. So if we go to the create info, pset layouts. Is a pointer to an array of vacated descriptor set layout objects. Pointer. Vacated descriptor set layouts. Alright. Alright, so we're just gonna create a fake array for now. So const descriptor set layouts is equal to vacate.descriptor set layouts. Well, actually I think we're just going to do something like this and then basically make it an array here. Const vacate.descriptor set layout, and hopefully right here we would say descriptor set layouts.ptr, and then in the other guy, which is set layout count, is equal to descriptor set layouts.len, I believe. So yeah. Alright, nice. So let's see if this works by any chance. Yeah, seems to work. Nice. So let's see if this is correct. Okay, so create pipeline layout. As you can see, vacate success. And the destroy pipeline layout, it's working out. Amazing, perfect. So next up, it would be the, well, right now we could go with the pipeline cache, or we could just leave it out. But honestly, it's fine. Let's just do it. I think it's not too much. Yeah, for sure. So const pipeline cache. Let's go. You could leave it out as null, by the way. But yeah, this is good for performance nonetheless. So I think honestly, I'm just going to copy this stuff again. Right, nothing too new for now. So pipeline cache. Cool. So handle, it's going to be the pipeline cache here. The device, the allocation callbacks. Let's go. Alright, so no need for this anymore. Here, instead of create pipeline layouts, we're gonna go with create pipeline cache. No need for this stuff for now. And here, destroy pipeline cache. Let's go. I believe this is pretty much it. Let's see. You give it the device, and then the allocation callbacks null for now. Let's go. And then of course the fur pipeline cache.dinit. Nice. Let's see what's gonna happen here. Of course, I forgot to actually load those functions into the device. So let's do that. Well, create pipeline cache equal to true, and destroy pipeline cache is also equal to true. All right, nice. Now let's try it out again. And there you go. There you go. Create pipeline cache, vacate success. Nice, nice, nice. All right, cool. Now we can actually load this pipeline cache and save it into a file. So basically when the user kind of creates the, runs the application for the first time, it's going to take a bit of time to actually create the pipelines. But afterwards, you're basically going to actually cache those pipelines and save them to a file. So when he runs the application again, it would kind of be just like instantaneous because it's already saved, basically. So yeah, that's what we're gonna do, I guess. So pipeline layout, pipeline cache. Okay. All right. Well, I think we're going to go with let's see. So I think we're gonna have a fn, maybe save function, or well, just get data function. Okay, self, and this would give you a U8 slice, I believe. Okay, and then we need get pipeline cache data. Okay, this guy, vacate get pipeline cache data. Data can be retrieved from a pipeline cache object using the command. You give it the device, the pipeline cache, the data size, and the pointer to the data. Okay, cool. So let's use that. All right. So how are we gonna do it? Well, of course we need the function. So get pipeline cache data is equal to true, and let's go back. So here's how you get the data. You say, right, so self.device.vkd dot, well, get pipeline cache data. You give it the device, of course, dot handle. That's our own abstraction, and then you give it to the pipeline cache, which is self.handle, and then the p data size. Now this works similar to all the stuff that we used before. First of all, you pass in null, you give it some kind of count here, so var count u32 equal undefined, and then you basically give it a reference to that count, and it would put the count of the data right around there. And here's self.device.handle though. And afterwards you have to call this function again, so let me just copy it right away just so I don't forget it, as I mostly do. And of course, after you get the count, you have to basically allocate memory for it. So here we're gonna say allocator. Now, other than allocator, there's also the other way that you could basically give the user the ability to give you a slice themselves to put the data inside. But honestly, never really thought about what would be the real difference there. But anyway, allocator. So scd.mim.allocator for now. Let's go. And const here, well, the data is equal to allocator.alloc. And here you give it the type, which is going to be U8. It's going to be just bytes. And of course the count, or should I say the size of the data in bytes. So yeah, there you go, size. You allocate, of course, you have to try stuff up, and you have to make sure to say error defer. So when an error happens, before we actually return from this function, we have to make sure to actually, well, allocator.free data. Otherwise, you have a memory leak when an error happens. So there you go. And let me make sure to do this. Okay, now afterwards, you basically call the same function as we always did, and then you pass in your new allocated data's pointer, and it would put the data right around the corner, right around there. Okay, so get pipeline cache data. This could fail, so let's make sure to say try. All right, cool. Well, and I think you basically afterwards you just return the data that you got. That's how you get the data of the pipeline cache from the driver. Cool. And or maybe we could even use a writer. Well, no, actually, never mind. It's fine. So, okay, so afterwards, well, we need somehow to basically save that pipeline cache. So I think maybe I'll just have a save function here as a helper function, I guess. So fn save, and then you basically maybe give it a subpath, I guess. And then the subpath would be a const u8, so basically a string. I always forget how to do that. Okay, there you go, const u8. Let's go, and then it's going to be, well, it's either going to fail and it won't return anything, I believe, isn't it? Yep. So yeah, so save. Well, here we're going to open a file, basically. So how we're gonna do that? Well, const file is equal to std.fs dot open file. Or we could say std.fs.cwd, which is basically the current working directory. And then maybe we could use that. Or honestly, hold on a second, what this gives us? This gives us the directory. But anyway, for now, we're just hard coding stuff anyway. So std.cwd dot save file, I guess. So sorry, open file or create file. Does it really have to be create file? I mean, what's the real difference between create file and open file? Because open file actually goes ahead, and if it doesn't find the file, I think it basically creates it anyways. But anyway, let's just say create file. You give it the subpath and then the flags. Well, the flags going to be, well, none. And then of course the fir file dot close. And that's how you open a file, I guess. You create a file, sorry. So now we have to basically write into it. Now I already have done that in the other project. Let's have a look. And so you just say try file.write all, and then you give it the data, seems like. Try write all, well, file.write all, I guess. And then you give it the data that you want to write, and the data in this case is going to be get data. Well, self.get data. And then here you should give it an allocator, I guess. And for that, I think we're just going to get an allocator. And of course, we need the self. Cool. All right. Well, here we have to give it the allocator. Cool. And hopefully that's it, maybe. Maybe. So let's see if this works, I guess. So afterwards, you'd basically say, well, defer. So pipeline cache.dinit, but also before we dinit the pipeline cache, we'd like to maybe save it. So pipeline cache.save, save to a subpath. Well, let's maybe call it for now cache, I guess. Pipeline cache dot bin maybe. Okay, and then here we would give an allocator. Okay, let's just give it our allocator right there. And if an error happens there, we don't really care. I mean, it's not the end of the world if you cannot actually save the pipeline cache. And also, handling errors inside of the for blocks is kind of tricky. So, well, I'm just gonna say catch, well, do nothing, I guess. How do you do that? Well, catch, do you say something like this? I don't know, honestly. But yeah. No field or member function named write all in. Oh yeah, I have to actually try this out. Oh, it's actually usize because it's coming from the driver. It's not really the API. Anyway, so here this should be usize actually, not U32. Let's go. Function cannot return an error. Oh yeah, it can now. Value type vacay result ignored. I don't care. And I don't care. Alright, expected type const u8. Found return type. Oh yeah, we have to try this one too. And we got some problem here. Memory address leaked. Oh yeah. Well, how do you actually not leak it? Let's see. So we have to make sure to take this data. It's very easy to leak memory. Defer allocator.free data. And yeah, seems all good. Let me see if we got our pipeline cache, and there you go. We got it. There you go. This is the pipeline cache. It got saved. Nice. But now I have to, of course, make sure to load it. Because saving it is kind of like just saving it doesn't really make any sense unless if you're gonna load it though. But yep, so load. And for this one, well, this one kind of, so basically I think what we're gonna do here, let's see, this should kind of like, okay, maybe instead of init you can say basically load, and then it's kind of basically similar to this maybe. So if n, well, honestly I think let's just do it. Let's just have some kind of function here called load. And in fact, I already have it here, I believe, maybe. So you just say read file contents, I think. There you go, I already made this guy. So it takes a subpath, an allocator, and then it goes ahead, it opens the file, it closes the file after it's done, then the metadata, it tries to get the metadata of the file, it makes sure that the file is an actual file, not just directory or anything like that, because well, in Linux everything is a file. Even devices are files. All sorts of things are files in the Linux world. So better be safe than sorry right there. And then return file.read to end alloc. We give it the allocator, then max bytes, I don't care about that, at least for now. And then there you go, read file contents. So let's try to use that one. So it basically gives us the data there. Now of course I have to modify my init function here, and well, okay, well. So here it would take a U8 slice. I guess maybe U8. Well, let's just do this. And this will be the data of the pipeline cache. And right here, when we create the pipeline cache, we could actually tell it about that. So how we're gonna do this? Well. Let's go back to vk get pipeline cache data, I guess. No, actually, vk pipeline cache info, I think. Okay. Where is it? Vk create pipeline cache. Okay. Vk pipeline cache creates info. Okay, so you give it the initial data size, and then you give it p initial data. So let's go ahead and do that. Initial data size, I believe, is equal to data.len, and then .p initial data is equal to data.ptr maybe. And let's try this out, I guess. But of course, so pipeline cache init, and I should give it data here right now. So you could, for example, give it no data like this, and let's see if it works. Yep, it seems to work, I guess. Get pipeline cache. What the? Hold on a second. Why there is two vk get pipeline cache data here? That's weird. Why we're calling it? Actually, not even twice. 3 times. Oh, never mind. It's create pipeline cache. What? Why are we calling it twice? Weird. Seems like somehow we're actually calling pipeline cache data twice. Oh yeah, we're calling it twice because of, yeah, to get the size and then to get the thing. Alright, gotcha, makes sense, right. So that works, okay. Now let's actually load the pipeline cache.bin right there. So how we're gonna do it? Well, init, now const data is equal to read file contents, and we're just gonna read the same file here. Then here it would give the allocator. Okay, and this of course could fail. And if it fails, we're just going to return, well, an empty slice, I think. So yeah. Now let's just give the data to the pipeline cache. Alright, so what's going on here? Should I do like this or something? Read file contents. Well, how do you actually do that? Let's see. Well, let's just say that this guy is U8. Const U8 maybe, and then well, actually, I think there is no need for const maybe. So why just memory address leaked, so I leaked some data. Yeah, I think data itself, right? Gotcha, okay. Well, yeah, I see what's happening here. Nice. So I think I'm just gonna say this, basically. No need for this crazy stuff. And then I would just say if it was successful, then what we're gonna do, and of course it would give us the data. Okay. If it was successful, we're gonna set it. So I guess I'll just call it bytes. Or since we called that contents, let's just call it contents. And then here we could say data is equal to contents, I guess. Alright. And then afterwards, maybe we could just check the data.len. If it's greater than 0, then we have to make sure to actually de-init it. Maybe check it out if you want. Okay, sure. Discord. Where is it? Codotaku? Project thread. Oh. Zig. There you go. Though you might want to try eliminating allocations when copying data between files. I just noticed those emotes. Oh man. Alright. Though you might want to try eliminating allocations copying data between files. If so, here's a nice way to copy contents from one file to another via FIFO, aka ring buffer. But the thing is, do we really have here two files that we're copying? I mean, I think we have only one file right now, and we're basically exploiting those data using the API into the driver, isn't it? Oh, there is a TMP there. Is that like... Oh, but that's testing, isn't it? Yeah, that's part of testing. Try create file. Why this read right here? I think, do you mean read only? Const contents f1.write all. Oh yeah, so there is an API, and it's basically limiting what we can do. For example, if the API didn't actually work with buffers, read is necessary if you want to enable reading. Oh. But I think if you're using create file, right? Isn't it? I think you mean when you're creating a file. But I think when you open a file, it's already read. It could be readed without that. But basically the API almost always requires, there is some other functions, but mostly it's basically gives you a count, and then you have to go ahead kind of try to prepare some buffer with that size and for that type, and you would just call again the API and it would go ahead and fill up for you that thing. So create file only enables writing by default afig. Yeah, I gotcha. Makes sense. Makes sense. But here we're using open file in my, at least in my code. So yeah, pretty cool. So now if data.len is greater than 0, then we have to make sure to deallocate that stuff. Allocator.free and the data. And let's see now. Oh yeah, of course, error, else, error. So you capture an error right there. Let's go. In used capture. What do you mean? Oh yeah, let's just do this to ignore the error. Cannot assign to constants, of course, var. And zig build run. And it seems like we have some craziness going on there, I guess. Oh yeah. Segmentation fault. Pretty cool, isn't it? Oh, defer allocator.free. Defer if data.len. Okay. Let's see if, what about that? Okay, I think that works right now, isn't it? So vk create pipeline cache, as you can see, initial data size is 36. Yeah, I guess it works right now. Amazing, perfect. And of course it doesn't error when the cache is not available or have failed to save or load, basically, because cache is not a big deal to load it, etc. So yeah. But hold on a second. Const pipeline cache init. Alright, nice. TLDR, the highlight of that is FIFO.pump, which is just use a buffer to copy from any reader to a writer. Yeah, makes total sense. So FIFO dot linear FIFO static cd.mem.page size. FIFO.pump f1.reader f2.writer. Nice. That's cool. And define. Why are we using X here? Const amt ft f2.read all. Okay. Cool. Alright, so I think we got the pipeline cache down right there. So yeah. But maybe we could put that into a save function instead. But anyway, for now this is fine, I guess. So what's next? I think right now we could IDK is just a quick way to type 256. Oh, I see. So now we got the pipeline cache and the pipeline layout. Now what's needed is the actual pipeline itself. All right. So. Now, pipelines are kind of interesting because, I mean, you could create one by one, but it's not the best in terms of performance. Ideally, you'd have to create a lot of them in a batch, okay? So that's the most performant way, as far as I know. And even in the API, you don't have create compute pipeline. You have actually create compute pipelines. So it is expecting you to actually create compute pipelines in a batch instead of one by one. Although it would work fine if you do so, though. But yeah. So instead of having maybe, well, let's see. So maybe we could have compute pipeline equal to a struct, right? Or actually pipeline in general, right? Just like I did before in the other live streams. So you'd have a pipeline and then you'd have maybe compute pipelines kind of struct thing. And this would be the batch basically. Because a compute pipeline and the graphics pipeline or whichever actually gives you, at the end of the day, it's just a vacate pipeline. The only thing that changes is how you create those pipelines. For graphics, you actually use create graphics pipelines, but for compute, you use create compute pipelines. But the end result, which is the handle, is just vacate pipeline, and you destroy them the same way, etc., etc. And so yeah, so here const pipeline, how we're gonna do this? Well, let's actually just copy one of these guys real quick, honestly, and let's just call it pipeline. Okay, here you'd have pipeline. Notice that we don't have compute pipeline here, just pipeline. Doesn't matter. And yeah, device. And this would really serve just as kind of like a container for the pipeline. It won't really take the job of creating them. So we would just get the handle right ahead, just like this, and we would just set it. You would just say handle, as simple as that. And then here you would say destroy pipeline. Notice that we don't have here destroy compute pipeline or destroy graphics pipeline. You just have destroy pipeline. You give self.device.handle, self.handle, and self.allocation callbacks. Nice. Nice. Cool. Well, now let's go to the compute pipelines, I think. And here where we're going to have the cool stuff. So you would say init, I guess, or well, let's say const self, or honestly just copy this stuff. But some things would change here. So compute pipelines. Now this, of course, as always, device and allocation callbacks. But here we were going to have a slice of pipelines, and this would be the handles, I guess. And then here in init, you give it the device. Now instead of the handle, we're gonna have some other stuff, I think, which is, I believe, if I remember well, vacate.compute pipeline create info, right? Exactly. It would be a slice, of course. Missing parameter name. Oh yeah. So these are the create infos. Well, infos. Later on, we'd like maybe to make this better. For now, it's fine, I guess. And here, handles, well, equal handles, but of course, we still didn't have that yet. So. Const handles, I think let's basically allocate memory for this guy. And how you would do that? Well, you need the allocator. stdmem allocator, let's go. Okay. Is equal to allocator.alloc. And then here the type is basically vacate pipeline. Just like this. Oops. Pipeline. And then the end would be basically the count of how much infos we have there. Infos.len. Now, of course, error defer handles dot, well, actually allocator dot free handles. Nice. Let's go. Now in the init, after destroying all the pipelines, so Oh well, honestly, honestly, there's no need for this guy for now. Anyway, let's just remove those. So here we would just go through all the handles that we have. But of course that means I also have to store the allocator. Otherwise I risk the caller giving me another allocator than the one he used to allocate, which is going to be bad. cd.mem allocator, let's go. And here I would basically store that allocator is equal to allocator. Oops. Alright, so for handles, in handle, but of course self.handles. Okay. So here I would basically say this. But of course here instead of self.device, well, self.handle, I would just say handle in this case, and there you go. Now after destroying all the pipelines in that array, then we can free the array. So allocator, well, self.allocator .free, and then you give it the handles array to free it. Otherwise, if you do this first, then you do this, then you're gonna have a big problem, which is that you're going to loop through, well, freed memory, so it could be invalid or even corrupted. But anyway, whatever. Compute pipelines. So now I think this is well, not really it. Hold on a second. Here defer allocator.free. Then here we have to call let's see, well, device.vkd.create compute pipelines. Let's go, and here you give it the device handle, and then the pipeline cache. Well, we already have the pipeline cache, so that's nice. So, well, let us take that too. Later on, we have to think maybe about some guidelines for how we order the fields, how we order the arguments, but for now, it's all just a mess for now. So anyway. Okay, create info count. Here would basically be infos.len, and here infos, I believe, .ptr. Now the allocation callbacks, let's go. We already have that one. And finally, where to put the pipelines? Well, in our allocated thing right there. So we're gonna say handles.ptr. And there you go. Now, of course, this could fail. So we're gonna say try create compute pipelines. And as simple as that. Let's see if this would work by any chance. So, of course, let's try to create a pipeline thing. So const pipelines, I guess, is equal to, well, okay. Compute pipelines is equal to compute, well, compute pipelines dot init. Here you give it the device, and here you give it the infos and the pipeline cache, the allocator, the allocation callbacks. Of course, I don't know why ZLS is broken right now, but anyway. Expected that, found that. Well, yeah, infos here. So here I would just say, I guess, this, and allocation callbacks null, and use local constant, and of course after that defer compute pipelines.dinit. All right, cool. So do we even have the init? Yeah, it does. Right, there you go. Cool. Now this should be an array of infos. So how are we gonna do it? Well, or should I say slice of infos? So let's see what we need here. I guess shader stages, right? Isn't it? Let us see. VK compute pipeline. There you go, create info. So we have all this stuff, but what's interesting is the stage, the layout, and the other stuff we don't care about it. The layout is pretty simple. Layout is equal to the, well, pipeline layout. And then the shader stages is what interesting here is, well, dot stage is equal to, well, vk.pipeline stage create info, right? Or we could basically say this, right? And then dot stage, let's see what's going on with that guy. So this would be, you would give it the module, which we already got. So module equal to shader module dot module. Well, dot module right there. And then what other thing that I'm interested into is the stage. So here you tell it what kind of module this is. Well, in our case, it's going to be a compute module. So vk compute bit or vk shader stage flag bits. There you go, flags dot. Here I would say, I guess, compute, if I remember. Hold on. Yep, compute bit. So dot compute bit. Oh, actually it's a struct, okay? So you say this, and then you say dot compute bit is equal to true. And there you go. Okay, I think this is pretty much it for now. Maybe. Let's see. Zig build run. And of course there is something weird. Oh yeah, I forgot to actually load the function pointers that we need. Well, get pipeline cache data. Well, here we need create compute pipelines. Let's go is equal to true. Destroy compute pipelines. Destroy pipeline is equal to true. Let me make sure I have done it right. Yeah, I've done it right. Okay, cool. So let's see if this would work now. Consider using try, of course. I always forget. What do you mean? Oh, not module here, handle. Okay, what else? I think I probably need const here for now. Expected type, oh yeah, pipeline layout handle. P name, oh yeah, I forgot that too. So P name, there you go. So with the module, P-name is basically the entry point of the shader. So P-name, well, P-name like this is equal to main, because our entry point is main, if you remember. So here you go, it's called main. So basically you could have, like, I guess, a Uber shader where you have multiple entry points, and yeah, every shader stage you could use another kind of entry point. So you basically compile one shader and you use one shader for everything. You can do that with Vulkan, I guess. So, although I never really tried it, honestly. Okay. Handles. Well, I think I basically missed one thing there. Consider using try catch. Yeah, compute pipelines.init. It can return. So we should just make sure to say try. And what else? Missing struct field base pipeline index. Oh, that one doesn't really have a default value. Well, that's crazy. So I would expect it to have that, but well. All right, so let's see. Vacate pipeline, create info. Yeah, it doesn't have a default. Crazy stuff. Okay. Base pipeline index, right? Yep. Sure. Easy. So main.zig, and let's add that. So after I get the stage, yes. Basically, it's well, where is it? It's right here. Okay, so base pipeline index. We could just make it 0. The other stuff have default values. So we're passing some handles here into yeah, I think it's because of the allocator, right? Isn't it? Yeah, I have to do try. Find main.pipeline cache. Oh well. Dot handle here. Infos.len should be casted. Well, hold on a second. Let me add a comma here so it formats it for me. Nice. Lovely. Much better. Much better. So now let's say as, or intcast, actually intcast, right? And then you'd say u32, and then you'd cast that to u32, okay. Cool, zig build run, expected integer or vector found. Oh, not here. Not here, let me do it here. So let's go. Okay, Vulkan of type. Let's ignore that stuff. Seems all good now, I guess. And my fuel is done. So, let's see if this is working as I expect. So as you can see, vacate create compute pipelines is being called, and it's actually getting vacate success. We're passing the device, the pipeline cache. Pretty cool stuff. All right, seems all good, honestly. Yeah, seems all good to me for now. Nice, amazing. So I wonder how big is the pipeline cache. So pipeline cache is 4.7 kilobytes, I guess. Remember that before we actually have created the pipelines, it was something like in bytes, kind of like 36, I guess. 36 bytes if I remember well. But right now, after creating the pipelines and stuff, it's 4.7. Right. So pretty cool. Okay, so other than this, right now what we have to do. Now, we basically have created our compute pipelines, which is amazing. So now we gotta, I think, start creating the command buffer and stuff like that, so we could basically send commands to the GPU so we can process it. Until now, we haven't really touched upon the GPU really. It's just the setup stuff. So, but pretty cool stuff nonetheless. So, yeah. Okay, any questions up until now? Is someone still didn't sleep yet? Is someone still awake with me? Right. Compute pipelines. All right, well, let's go ahead and I guess start creating the command buffer and cool stuff like that. Honestly, hold on a second. I'd like to do something real quick. Just have a look. Which is to go to my repos and let's have a look into Ash stuff, for example. So here's my Vulkan implementation in Rust. What is that toStream just to get close to actually using the GPU? Vulkan. Oh my god. So here's the Vulkan implementation in Rust using Ash binding. That I think I have a video on that, right? You could like check it up if you want. So here's the device queues. We got them. Then afterwards I created some, but although I did use a lot of crazy libraries, for example a library to make it easy to create buffers, but yeah, anyway, creating synchronization objects, command buffer. So right now we're going to need the command pool, the command buffer, defense, and yeah, we're just going to write down, I guess, just fill up the commands, and then we're going to submit to the GPU, pretty much. And then of course after that, after everything is working fine, we're going to of course edit the shaders so it can accept some buffers and it can do some operations on those buffers in parallel. And then of course for that we have to basically allocate, look up on how we can allocate buffers, map them, etc. using Vulkan. So there is a lot still, but we're very much not that far. But anyway, so let's go with the command pool now, I guess. So compute pipelines, read file contents, man. Like I wonder how much languages I actually implemented Vulkan in at this point. So I implemented it in C first, I believe, if I remember, and then I implemented it in Rust and a bit in C++, although I don't think I completed that one because C++ just drove me crazy. So that's when I actually used C instead, and I was pretty happy with C. although it's shortcoming. And now in Zig, and honestly I enjoyed Zig on all of them, from all of them. It's pretty cool language, honestly, especially for graphics programming so far, so that's pretty nice. How was the Rust implementation? Rust implementation wasn't that great, honestly, because as you can see here, every time you have to use unsafe code, and unsafe code is basically more unsafe than Zig itself. So as you can see, a lot of unsafes right there. So pretty much, you know, like the selling point of Rust is being safe, but when you're dealing with drivers, you know, when you're dealing with the graphics drivers and all this crazy low level stuff, you're pretty much gonna have unsafe code everywhere, which is honestly very painful and very error prone. But Rust is a pretty great language for safe code. Still my favorite for safe code, and also I really love its build system. Like so far, Rust's build system is pretty much far the best, and also the ecosystem of Rust is the best, at least so far. Hopefully Zig would go in a similar direction. That would be very great. So yeah, pretty much. Graphics context. For example, if you'd like to deal with images, you just say cargo add image, and there you go. You have the library you need, you know. So it's pretty cool, honestly. All right, so now let's go ahead and create a compute, well, not compute, but command buffer, command pool, sorry. Okay, cool. So let's go ahead and do that. Well, so I'm just gonna have the same kind of boilerplate code for Vulkan objects. So const command pool. Okay, cool. Self here, this is going to be command pool. Let's go. The device allocation callbacks. No need for this. And no need for this, although here we would have create command pool. Let's go. And I think it's pretty much kind of similar stuff right there, but of course let's check out the documentation of command pool now. And here of course destroy command pool. Oops, destroy command pool. You give it of course the handle, the device, and the allocator as always. So this is pretty much it. Now let's just check out on the documentation. Vacate command pool create info. Let's see what we require there. So we require Q family index and the flags. So let's have a look at the flags real quick. Yeah, this is pretty interesting. So maybe we may use this one because it will be short time frame, I guess. You don't have a loop similar to like graphics Vulkan stuff. We will just basically do something and then just deallocate everything, and then you're done. Vacate command pool create reset command buffers. Okay, so for now let's just pass in the Q family index. Designate a key family as described in section key family properties. All command buffers allocated from this command pool must be submitted on queues from the same key family. All command buffers allocated from this command pool must be submitted on queues from the same queue family. Alright, cool. So you have to basically create a command pool for each and every key family that you'd like to use. Cool. Alright, so here we're gonna have the index stuff. So queue family, well, queue family index is going to be a usize, and then here you would say dot queue family index is equal to int cast u32 queue family index. And yeah, I think this is pretty much it. And now let's try to create a command pool. Const command pool is equal to try command pool dot init. So here you give it the device, and then you give it the queue family index, which is going to be our queue family dot family, I guess, or yeah, index actually, I believe. So allocation callbacks null, and then of course defer command pool dot dinit, and let's go. Let's see if this would work. Hopefully it would work from the first time. There you go. Okay, so I forgot to load the functions. Oh man, I don't remember myself just writing some code in Zig and just it would compile directly. But at least that's better than JavaScript and Lua and other scripting languages where you wouldn't know what's wrong with your code until you reach that point where the code isn't bad. So anyway, I pretty much cannot really work as a programmer anymore without a static analyzer, like without having compiler work with me instead of just having the bug pop up into the user screen. So anyway, never mind. Alright, so destroy pipeline here creates command pool is equal to true, and destroy command pool. So this is all the API functions that we have used so far. Alright, pretty crazy stuff. So now hopefully it would work directly. Nice, it works. Cool. So let's see if everything is good so far. Okay, so as you can see, vacate create command pool, vacate success. Nice. Amazing. Very cool. And also, let me actually switch to validation just to make sure I'm not doing something crazy. Yeah, no validation messages so far. Although we'd have to optimize later on for allocations to remove some allocations out of the thing. But anyway, so other than this, let's see what we got next. So right now I think we need the command buffer, and the command buffer you allocate it from a command pool. Okay, so well, similar thing, although not really the same exact thing. So command buffer, let's go. This will be a command buffer. So command buffer is kind of special that you do not really create it, you just allocate it, and you do not have to destroy it. You basically just destroy the command pool that you used to allocate it with. So it's kind of like you creating an allocator when you create a command pool, right? Similar to Arena, basically. Command pool is similar to the Arena allocator, and then you use that command pool to allocate command buffers, pretty much. So here, instead of create, you say allocate command buffers. And again, you can see that the API is suggesting us to actually allocate command buffers at the same time if possible for best performance maybe. So we're gonna do, I think, the same strategy that we have done with I believe the pipelines, just to make sure we're not compromising on performance or convenience, I guess. So anyway, unless if we have some problem with that later on, but anyway, this is fine for now. So allocate command buffers, what it takes? Well, it takes a device, allocate info, and p command buffers. Okay, cool. So this is pretty much similar to the compute pipelines thing. So honestly, let's start from there. Let's do something similar because it's going to be very, very similar to how we've done it there. Okay, so const here command buffers. So this is kind of like a command buffers batch. Okay, and here vk.command buffer. Let's go. And we do need an allocator, right? And we do need the infos, I guess. Maybe. Yeah, I think. But of course, instead of compute pipeline create info, we're going to go with command buffer allocate info. And let's go. And we don't need, of course, a pipeline cache in this case, and allocator and allocation callbacks. Right, pipeline cache. So here allocates command buffers. Now let's see what we got. So of course, no pipeline cache. Now let's see what we need here. So allocate info, a pointer to it, and p command buffers. Yeah, okay, so here you basically say infos.ptr, right? Right, I guess. Allocate info. And then here command buffers. Well, let me see the whole thing honestly. So you give self device and command buffer allocate info stuff, and then command buffer. All right, cool. So you don't need the allocate stuff. Yeah, seems like you don't need allocation callbacks, which honestly makes sense because it's using the command pool in this case to do that stuff. And I don't think we need to dinit, right? Basically, to dinit a command buffers, you basically just destroy the command pool. That's basically how it goes. But there is something, I believe, if I remember, there's like, you could actually reset the command buffers or something like this. But of course, we do have to free the allocate, the array that we're gonna use to actually hold the command buffers, of course. But we do not have this stuff. So let's see. Okay, so here we need the command pool. So we're gonna put that, well, we could do it here, I believe. Command pool. Command pool, well, okay. vk.command pool. Let's, well, actually just command pool, right? Let's go. And that's it for that one. Now you allocate memory for command buffers with the length of course, the infos, or isn't it? Hold on a second. Let me, actually, not really. What? Hold on. So command pool create info. Let's look for vk create command buffers. Sorry, allocate. I need a refresher on this. So you give it the allocate info. Oh, so you have one allocate info. Yeah, that makes sense. Yep. So one actually one thing right there. So info, and you just, I guess, say vk command buffer allocate info. And here we cannot use infos.len though here. So we would basically have to specify ourselves how much command buffers we'd like to create. And so you're gonna have, well, actually you would get it from the info, right? You'll get it from the info. So you give it the command pool, the level, and the command buffer count. So honestly, in this case, we don't even need the info. Well, let's just go with the count of how much command pools you'd like. And that would be, well, I guess usize. Well, let's go with U32, I guess, for now. Okay, cool. Now you basically pass in the count here. Okay, cool. Now allocate command buffers. Here you give it the allocate info. And for some reason you have to actually pass the pointer to it. Weird, but okay. Maybe I'm missing something, who knows, but fine. So I would say here, well, I would say this. And then I need the command pool, which is going to be the command pool.handle. And I'd need the buffer level, which is going to be, is that a struct again? No, this time it's an enum. I would go with a primary command buffer. Okay, and then command buffer count. And I would give it the count here. Okay, and here I basically give it a pointer to the stuff that I allocated, the array that I allocated, and yeah, pretty much. And then you store the handles, the device, the allocation callbacks, the allocator, and maybe also the command pool. Although, hold on a second. Is there something for the command pool stuff? I remember there's something maybe like reset command pool or command buffer, something like that. Yeah, there's vacator set command pool. Let's see that one real quick. Yeah, but this actually is for the command pool, not command buffers. So we don't really need to honestly store the command buffer for the command pool for now. So yeah, that's fine. Cool. You're just going to free the handles array. And that's pretty much it, I believe, for command buffers. Well, let's see what we got now. Const command buffers is equal to try command buffers dot init. You give it the device, the command pool. You give it the count. Well, how much command buffers I would like. I guess for now, just go with one, I guess. Allocator. And here, we'll just pass in the allocator, and here, null. And of course, the for command buffers dot dinit. Oops. Dinit. And again, I forgot to actually add those stuff. Dot allocate command buffers equal to true, and dot deallocates, or what I'm doing. Yeah, I think that's all we need. Yeah. Cool. Okay, so it works. Now let's see if that works as I expect. API dump real quick. Sig build run. Alright, destroy. And as you can see here, we're actually creating the command pool. Then we're allocating command buffers. And as you can see, vacate success. Nice. So, okay, so we have right now a command buffer. And we also have that guy. Cool. So now what? Well, we have to record commands into our newly created command buffer. So we're basically, now the thing is that you should understand here, when it comes to working with drivers and low level like this for performance reasons, the fastest way to exchange data between processes, you know, between two applications, for example, or between the application and the OS, or between the application and the driver, the fastest way possible is not through API calls, is through basically using that API call to get to map memory to that other process, to map your own memory into another process, or that process would map memory to you, or something like that. But anyway, but basically you share some memory buffer, some place in memory, and then you exchange data through it. And now a similar kind of thing is with GPU stuff also. Now GPU, as you know, like there is a long way to go between the CPU and the GPU. So to get data from the CPU, or the RAM should I say, to the GPU, there's a long distance. I mean, if you're taking into account that you have stuff going on in the speed of light, man, if you're on that scale, it's like, I don't know how to describe it, but it's very, very long distance. So if we'd like to basically transport one bit after the other, or one byte after the other, or one command after the other, like in OpenGL, for example, although OpenGL, the driver is doing some batching internally and it's doing its stuff. But let's just consider that OpenGL doesn't do those optimizations in the driver, for example, okay? Just for the sake of example, let's say you really, when you actually call a function in OpenGL and there is no optimizations in the driver that would, you know, like batch the buffers, etc. So what's going to happen is that you're going to need to basically transport data from the CPU to the GPU one after the other. So here's a pretty cool example in real life. Let's say you have a truck, okay, and you have some stuff to transport from one city to another, or heck, why not, even from one country to another. So will you just take one box and then transport that box, come back and take the other box and keep on doing like that? Yeah. That doesn't make sense, right? You're going to batch as much as possible. You're going to put as much boxes as possible that could fit in your truck, and you're going to transport them at once. So here you have batched all those boxes at once, and you transported them. And that's how basically we need to do it. You have to batch commands instead of sending one command after the other, or one data unit after the other to the GPU. We batch as much as possible, and it goes through the wire to the GPU. So yeah, pretty much that's how it goes. That's why we need the command buffer here. And so right now we're going to record commands into this command buffer, and then later on you're going to see that we're going to use our queue that we have created before to basically to send that command buffer to the GPU so we can execute it. Okay, so this is what we're gonna do. Well, let's see how we can do it. So vacay, hopefully that made some sense. All right, so let's see. So device.vacd. Now I need to refresh my memory on how you do it. Well, vacd, I believe, .vaccmd or cmd. Okay, so all the functions in Vulkan that starts with cmd, all of these are how you actually are basically commands that you could use, that you could record into your command buffer. Okay, so all of these are commands that you could use to tell GPU to do something, or at least the driver, and then it would do the rest. But anyway, so here cmd, and what we'd like to do right now, well, we'd like to bind a pipeline, I believe. Right, bind a pipeline. So let's see how that goes. So you give it the command buffer where you want to actually record that command. So in our case, command buffers, let's say, let's get the first command though. Const command buffer is equal to command buffers dot handles 0. Okay, and you basically here you give it the pipeline bind point. Well, what is that? Hold on. AK pipeline bind point. Oh, so it's an enum. Okay, so we're gonna go with compute because we have compute. If you're going with ray tracing, there you go, subpath shading and graphics. Now compute, and here you give it the pipeline. And in our case, we have the pipeline. So pipeline, well, compute pipelines, I believe, right? And here we're gonna take our compute pipeline. So dot handle 0. So here we're gonna say pipeline. Let's go. Use of a declared identifier command. And here we have to give it the command buffer. Okay, so now hopefully this would be used to record. And of course, as you can notice here, that when you're recording the commands, you don't get any results, okay? You don't get any errors or whatever. Now, when do you really get the errors is when you actually end the recording to the command buffer. But of course, before beginning to record to the command buffer, I just remembered, you have to first of all make sure that you're started to do that. So begin command buffer, there you go. And here you pass in the command buffer that you'd like to start. And here p begin info. Well, p begin info. Let's see what is this p begin info thing here. So it takes flags and inheritance info. So let's check this flags real quick. Vacate command buffer usage one time submit bit, usage render pass continue bit, and simultaneous use bit. Honestly, I remembered something which is very nice. Now, Volcano have a pretty cool documentation. Like guide, a Volcano guide, right? And in fact, I remember I contributed to this guide. So, oh, did they change it or what? Yeah, it seems like well, I guess they have changed the look, right? But I think maybe it's pretty much the same exact thing, isn't it? Alright, I think so, yeah, pretty much. So creating a buffer, example operation, introduction to compute operations, dispatch. Okay, so this is cool stuff. Okay, creating a command buffer allocator, creating command buffers, submission and execution. Where is it? There you go. They're starting a command buffer and they're basically using copy buffer. But no, we'd like to go with a compute pipeline stuff. So introduction to compute operations. There you go. Alright. Here they're creating a buffer. Compute pipelines. The scripture sets, there you go, and dispatch. Now this is what we need. Okay, so here they're creating a command buffer and we're group count. Okay, so the first thing is you bind the pipeline compute, as you can see. Then you bind the descriptor sets, which we don't have currently, and you dispatch. So yeah, pretty much. But yeah, begin. And you pass in one type submit in this case, right? So as you can see, render pass continue bit, simultaneous use bit. So I'm gonna go with this guy right here. So flags is equal to vk.command. Well, what kind of that thing is vk command buffer usage flags. Okay, so this is the kind of struct thing. Okay. All right, so one time submit bit is equal to true, because we're going to submit it once, pretty much. Specifies that each record in the command buffer will only be submitted once, and the command buffer will be reset and recorded again between each submission. Okay, cool. So here we're beginning command buffer, here we're binding the pipeline. And then next we have to dispatch. So vkd.dispatch, okay. Isn't it cmd dispatch though? There you go. And here you give it the command buffer, a group count x. Let's just use what Volcano is using. This is kind of arbitrary kind of thing, although there is some logic behind it, but let's not go into details right now. 1024 11, and let's go. That's cmd dispatch. And pretty much we have done with the commands that we'd like to send to the GPU, I think. And then we're basically going to end the command buffer, I believe. So device.vkd.end, well, yeah, the end command buffer. Guessing that's a packed struct. Which struct you mean? So end command buffer. Here we give it the command buffer. The flags, I mean. Well, it's from the binding. I don't know really. Yeah, it's a packed struct. There you go. Yeah. So instead of orienting flags, integers, yeah, you basically use the struct to turn on the flags that you'd like. But anyway, so end command buffer, and then, so pretty much end command buffer. Okay, so this could fail, of course. Now here where you actually get an error if you have misused some of the commands before, basically. But if you noticed, any function in Vulkan that starts with the cmd that you basically use to record commands doesn't return anything, void. Until you end the command buffer, that's where you actually get your result. Not the result of actually, here we're still just the result of basically recording the commands. We still didn't really send, we're just preparing the command buffer now. Okay, so I think we're done with the command buffer right now, but of course we have to basically load all of these functions. So we have used begin command buffer, cmd bind pipeline, cmd dispatch, and end command buffer. And honestly, let's use that defer function. So instead of, so you just say, after begin, you can say defer. But I cannot use try in this case. Interesting. So it's kind of tricky to handle errors when you use defer, honestly. But anyway, let's just keep it like this for now. Okay, let's go back here. Dot start command, begin command buffer, sorry, is equal to true. Then end command buffer is equal to true. and then finally, well, not finally, but cmd bind pipeline, I believe. Yeah, is equal to true, I guess. And then cmd dispatch. Later on, we're also going to need the descriptor set stuff to bind resources like buffers or images, but for now we're just trying the minimum to make this work. And so yeah, begin. I think that's pretty much it. Let's see. Error is ignored. Let's try this out. VK success, amazing. Good news. Pretty nice, lovely. Now we need the fence to synchronize our GPU and our CPU together. So basically the CPU is living in his own world, the GPU is living in his own world. They're like in different universes when it comes to the the speed of light. But basically they're working on parallel. Okay, so the GPU is working on his own side and the CPU is working on his own side. So you need some mechanism to synchronize them together. So basically, let's say you want to meet someone, and that someone, well, he's living his own life and you're living your own life, right? Now if you want to talk with that person, you have to basically call him, and you set up somewhere to meet, etc., etc., and then you go through it and until, anyway, never mind. So let's go ahead and do this. So the fence is a mechanism to do that, to basically synchronize the CPU and the GPU. So let's go ahead and create one. Fence is pretty much simple to, the boilerplate code right here. So instance, let's see. For example, let's grab this shader module and let's use that as a bit or maybe the command pool. Okay, let's go with command pool. Fine. Command buffers. All right, so instead of command pool now, we're gonna go with fence. So vk.fence device allocation callbacks. I don't know if I need allocation. Yeah, I probably do, but anyway. All right, create command pool. Now create fence. Okay, and of course you also have create info stuff right there. Let's watch out for that. Fence create info. And the only thing that is interesting here is the fence create flags. And there's only one flag here, signal bit, which could be used in some situation. I actually used it before, but for now we don't need that. So pretty much it's just going to be empty for now. Although there is better synchronization primitives than a fence in newer Vulkan versions. They are very busy, don't like to be distracted, and validate their privacy. Is that why they need a fence? So, well, you need somehow to synchronize them anyway. But yeah, we'll see. Anyway, so bad at describing that stuff. Destroy command pool. Destroy fence. Right. Self.handle, self.allocation callbacks. So create fence. Okay, so this is pretty much it, I believe, to create a fence. But of course, let me not forget this time to actually add that guy. So .cm, well, not cmd, but create fence, right? Equal to true, and then destroy fence is equal to true. I wonder how much time have passed at this point. 2 hours and a half. Oh man. Okay. And this is pretty much it, hopefully. Now let's create a fence. And hopefully this time I would get it at the first compile without errors. So let's see. Const fence is equal to fence dot init. You give it the device, you give it the key family index. So key family dot index, here allocation callbacks null, defer fence dot dinit. Let's see. Hopefully I would get it. Oh my god. Oh man. Oh yeah, I forgot the try. Okay. Alright, nice. So as you can see, vacate create fence successful. Nice. Alright, so we have created a fence. Now we have to use our queue to send the command buffer to the GPU. Okay, so how are we gonna do that? Well, I don't remember. Well, we'll see. So let's see. So we have the queue, right? So let's say device.vkd.queue submit, I believe. There you go. Nice, I got it. So here the queue that we got earlier, then the submit count. I'm only gonna submit one command for now, or one submit should I say. But as you can see here, Vulkan again is suggesting us that for best performance, you have to basically submit as much as stuff as possible at the same time. And of course, here's our fence. So basically what's going to happen here is that it would submit those stuff, right? That command buffer. And then when it's all done, it will signal this fence. Okay, so when the GPU is done, he will go ahead and he will signal the fence. Or it will signal the fence. And then here in the CPU, we're just going to wait for the GPU to signal that fence. And when that's all done, we're going to know that the GPU is done. Too simply. So anyway, let's see how that goes. So of course here we have a fence, pretty simple stuff. Now let's see how that works. Well, okay, queue submit. So it's an array of submit stuff. So let's actually create a slice for that, honestly. So const fences, well, vk.queue submit, I guess, or queue, what is it even? Submit info, okay. So equal to, here we'll have an array of stuff, and well, why call it fences? Submits. Here it would have submits.len. And then here we would have the submits. Well, just like that. Okay. Well, submits.ptr though. Cool. So now let's fill this up and let's see what we need. Okay, we need a lot of crazy stuff here. Okay, so at pnext wait semaphore count, we're not using semaphores here. Semaphores are kind of, well, they're also used for synchronization. It's also a synchronization primitive. But while fence is used to synchronize the GPU and the CPU, semaphores are used to synchronize, for example, you can synchronize two operations inside the GPU, you know. Or for example, to synchronize two queues inside the GPU because they're also in parallel, you know. It's like the GPU is just a big parallel machine, you know, so it's all parallel. Okay, so p-wait, we're not gonna use any semaphores. Range command buffer count, because we only have one operation that we're gonna do in the GPU, so there's nothing to synchronize in that matter. So command buffer count. Here we're gonna set 1. p-wait DST stage mask. And here we're gonna give it the pointer to the command buffers, and then signal semaphore count 0. And p signal semaphores. Okay, let's set this command buffer count and p command buffers. For now, let's just say 1. Let's just hard code stuff to keep things simple. P command buffer infos, or p command buffers, is equal to, well, command buffer dot handle. Should I give it a address like this? Isn't it? Or honestly, let's just go ahead and say command buffers dot handles dot len, and here let's just say command buffers dot handles dot ptr. So yeah, cool. Hopefully this is it, I guess, maybe. So this could fail. And let's have that q submit equal to true. And the moment of truth is the build run. And as always, of course, we need errors in our lives. Cannot cast pointer to tuple to vacate.submit info. Const. I guess I need const here for now. Okay. Yes. I forgot about this one. So int cast u32, comma, that guy. I need p-wait DST stage mask. I'm not sure if this really makes, like, it makes sense for fences. But let's just set it right anyway. So vacate wait DST stage mask, or what? Pipeline stage mask? I don't remember what is it. Anyway, let's see. Submit info. Actually, let me have a look into the submit info documentation, really, instead of going blind. Vacate submit info. Okay. So what this is again? p-wait DST is a pointer to an array of pipeline stages of which each corresponding semaphore wait will occur. Semaphore. Alright, so I'm just gonna set it to null. I don't care about semaphores. So null. Okay, is there anything else? Of course. Well, I cannot really set it to null. I need to set it to an empty slice, I guess. Maybe. Let's see. Well, let's have const stage mask or something. Anyway, who cares? Let's just say vacate.pipeline stage flags. Need a slice here, const slice, and I'm just gonna say is equal to this guy. Let's just say now this ptr. Yeah, q, where is q? Q.handle. Are this errors infinite or what? Submits.len. Fence.handle. Let's go. Nice. Let's see what happened there real quick. As you can see, the submit is success. Well, we have successfully submitted our command buffer to the GPU, finally. But we're doing a big mistake, is that while the GPU is still working on our submit request, on our command buffer stuff, etc., we basically just exit and let the driver figure out what to do with the response at that point. Crazy stuff. That's why you have to make sure to always say after submit, if you want to basically quit the application, make sure to defer vkd.quwait idle. Okay, make sure to wait for the queue to basically end. But we don't really need this in this case. We already have a fence that we could use in this case. So let's wait for the fence. Wait for the fences. Okay, pretty cool. Device.handle here. Fence count. We're just gonna go with fences.len. Here fences.ptr. Wait all. Do you want to wait for all the fences or just anyone? Let's go with true. Why not? I guess, or I don't know. Doesn't make sense. Doesn't matter in this case, as we're going to only have one fence for now. And here the timeout. Now you could basically wait for the fences infinitely, you know, or you could set a timeout here. I'm just gonna tell it, just take your time. We're not in a hurry, so I'm just gonna tell it, give it I believe scd.math.maximum int, and here I would give it the maximum u64, and this is basically infinite. So yeah, use of undeclared identifier fences, of course, because I still didn't do that. Okay, so let's have fences here. Honestly, for now, there's no need for defer currently anyway. Wait for fences. That could fail. Okay, cool. And let's see. Here we need const fences is equal to what? To a slice, right? So const vk.fence is equal to this guy, I believe. Right, nice. And then here, well, I'm just gonna go ahead and give it our fence. Okay, cool. Hopefully that's it. And let's try it out. And of course, I forgot again to load that thing. Wait for fences. Let's see, q. Okay, cool. Let's just say dot wait for fences equal to true, and now let's run this up. And again, as always, I forgot this. Int cast u32 fences.len. Oh yeah, it's a bool 32, not an actual boolean value, so we're gonna go with 1 or 0 right there. I don't care about the result, bro. Come on. Okay. And we're done, I guess. Yep, vacate success. We waited for the fence. Now let's just as a little thing, little experiment, let's see how much it would take for the GPU, like how much time we're going to wait for the GPU, like for the fence, basically, for the GPU to complete the operation. Let's see. Well, I never really used time in Zig. So how to do that? Well, std time, I would guess. Oh, instance is similar to Rust. Well, what about a nano timestamp? Or let's just go with milli. Okay, well, let's just say T1, like we're in a physics class. And const T2 is equal to... Can this fail, by the way? No. And I'm not sure if it's even the right one or not. Get a calendar timestamp in milliseconds. Okay. The return value is assigned. But we need a really precise one. But anyway, who cares? So std.print, .debug.print. And let's see what we get. So T2 minus C1. Milliseconds. And let's figure this out. I don't need the API dump. Let's go with validation instead. And as you can see, the GPU took 1 millisecond. Because it didn't really do anything, really. So this time it took 0 for some reason. Weird. So I think it's in the nanosecond range. Let's go with maybe nano timestamp, because really virtually the GPU is not doing anything really. Like maybe the driver is even just optimizing this out altogether, because we're not really doing anything meaningful right now. But we have managed to make it work. And of course that's not milliseconds now, this is nanoseconds. And as you can see, the GPU took 133,849. So that's cool, nanoseconds. Let's see how much it would take again. 144, 84, 75, 143. So of course it would fluctuate, because I'm not the only one who's using the GPU here and not the only one who's using the driver. But finally, at least we run something on the GPU, hopefully right now, at this point. Now, it's the time to actually make this do some meaningful work. Now, to be able to do this, we gotta first of all create some buffers, you know, which is gonna be not so easy. We gotta allocate some buffers, we gotta fill them with some data, and we're going to basically upload them to the GPU, and maybe we have to synchronize, possibly, and we have to create a, what is it called? What is it called? Hold on. Let me see. Hold on a second. I forgot even what they're called. Descriptor sets, right. We also have to set up descriptor sets. And we have to bind those stuff, etc. So yeah. .ns per s. But why the times 1 there? This gives you seconds. Is that times 1? Right, hold on. How much time is left? Yeah, just showing common usage. But why the times 1? Isn't times 1 right there not needed though? Like, I mean, what's the point of that? So it's already 3 hours. So right now I'm just going to at least commit this stuff right now. And then we could maybe try to start doing the buffer stuff. What happened here? Constraint add. Who knows? So, oh, builder. Oh yeah. Okay, I see. All right, pipeline cache. No need to save that. Just going to ignore that for now. Get ignore. Pipeline cache. Right. Pipeline cache. Oops, pipeline cache like this. .bin in this case. So get ignore minimal.com shader. Yeah, okay. And main.zig. Ooh, man. All right. Let us actually just see how much functions are there just to get something working, an operation working. So okay, let me actually commit this, and first GPU complete GPU operation. Although it's meaningless, it doesn't do any meaningful work, but at least we have actually done an operation. So let's just commit this first of all, and I believe let's sync the chain. Whoa, what? Why there is that guy? That's weird. Why there's a poll? What? What the? What's going on here? I did pull everything, so what's the problem? Well, do you remember it's like poll rebase or something like this, like that? Oh man, come on. Poll. Let's say poll rebase, I guess, and then let's. What do you mean by there are no changes to commit, man? Come on. Wrong repo? I mean, there's only one repo. But first of all, honestly, I just back up this stuff first. I'd like no surprises right now. Imagine, man, that would be another level. Let me first of all back up at least. Okay, so okay, let's see. CP Vulkan Zig compute to Vulkan Zig compute 2, or backup should I call it. All right, at least right now we have a backup just in case if something crazy happens. Let me make sure that's the case. Yeah. Yeah, seems it's good. So cool. Now let me go to my repo. Right, so certainly wouldn't like to lose all this work. Okay, well, right now what's the problem here? Now, can I push? All right, seems good, I guess. I just repoll and rebase, sorry, and then I just pushed. But just, yeah. So, where is that thing now? Where is that thing? Vulkan Zig. Well, let's go to GitHub. Well, where is that thing? Codotaku. Oh, Zig. Vulkan Zig Compute. And there you go, 2 minutes ago. And nice, seems to be working. Amazing. Perfect. I'm glad I didn't lose any work. Okay. So, nice. So, is there any questions before we go to the next stage? I wonder how much functions we have used of Vulkan. So until now, we have used, here's a 1, 2, 3, 4, 5. Well, from here to here, how much? Man. $22, 23, 24, 25, 26, 27. So we need the 27 functions to just do a meaningless operation. Bruh. That's crazy. So what do you think, guys, about Vulkan? Would you try to do this? Man. Alright, well, that is crazy. Travelex. Alright, well, I think we're going to right now check out on how we can create a buffer. Well. Honestly, now this project, I'd like to basically kind of manipulate images, right? Using the GPU. So I think we're going to try to set up another dependency, I guess, called Zig EMG. I believe. There you go. So I never really used this guy, but we'll see right now. We'll figure it out, I guess, hopefully. Add package path. So let's add this guy. This confirms what I've heard about Vulkan, that it's really tough to get started with. Yep, this is just the start, really. We haven't done anything crazy with Vulkan. And in fact, we're not even exploiting Vulkan's string right now, which is basically parallel computing and craziness like that. Currently, we're doing I've done the most basic but yet complete operation in Vulkan right now. So pretty much the most minimal thing I could have done, I guess. So yeah. CD submodules or lib. And then here I'm going to actually go ahead and say git submodule add And don't get me even started with actually drawing a triangle into the screen. Oh my god. I think you'd at least need maybe some, I don't know, honestly, I don't remember. But I would guess at least maybe 2,000 lines of code, maybe? I don't remember, honestly. Or maybe even 4,000, 4K maybe, I don't know. Anyway, because there's still a lot of extra stuff that you had to do. But yeah, so git submodule add. Now we could also look into using VMA instead of allocating buffers ourselves. But I wonder if I really would like to do that, because we'd add, you know, a C dependency, another C library. It's gonna be crazy. So, and in fact, it's not even a C library though. It's actually a C++ library, I believe. So I don't think I would do that. So yeah, fine. Anyway, I'd like to just do it myself then. Okay. So I added that submodule now. Cool. Let's go back into business. So here, build.zig. And hopefully it would work from the start right now. So how we do it? So this is a work in progress library to create, process, read, and write different image formats with Zig programming language. By the way, thanks to Snektron for the nice binding. Shout out to him, and thanks to M. LaRouche, which we're going to use his library right now, which would help us to read and write different image formats. So yeah, exe clone. So use Zig EMG in your projects. How to add it to your projects clone. Add a submodule. Add to your build.zig. So exe add package path zig emg / zig emg.zig. Check out zig emg. All right, well. Oh yeah, so he's using zig-qoi from master Q32 for quite okay image format. And honestly, fine, anyway, never mind. So we'll just go ahead and do it. More outdated build stuff. Oh yeah, man. Oh yeah. Well, let's see. Do we maybe have to create like module like this, maybe? And maybe would give the source file, which is in this case possibly this guy. Just a guess. I have no idea how Zig builds stuff works. So let's try it. I mean, yeah. So the source file, well, the source file. Let's see. Create module, and here, so this is the Zig EMG module, hopefully. And here dot source file maybe is equal to lib / zig emg / zig emg.zig, I guess, and then maybe exe.add module, and then zig emg, and then let's pass in that zig emg module. Hopefully this works. I'm just guessing at this point, so who knows. Yeah, that's true. Dot path. Let's see what we could do here. Well, cd dot build dot file source dot. Maybe we could say relative, and then maybe we could basically do it here. Seems to compile at least. By the way, can I do this? No, doesn't look like. Okay, well, now the moment of truth. Let's try to import it into our code. And I would be amazed if this works, because I literally just guessed it. So const zig emg import zig emg. Let's see at least if this compiles. Okay, but let's see if it really works now. I guess it works. Okay, let's see some example or something. Is there examples? Doesn't look like, but there is tests. So let's check that out. Honestly, I've never used this repo, so you have to use it to see if it worked because of lazy analysis. Yeah, exactly. That's what I'm trying to do here. So zig emg, would that make sure that it's actually working out? Wouldn't the compiler just optimize it out? Seems to be fine though, but right now we gotta figure out how this works. So you say image.create. Okay, let's try this out. Const image, but let me see the other stuff. Hold on. Looks good. No, that forces it to be analyzed. Oh, that's nice. Image create, cool. Analysis not equal code gen. I see. Yeah, that makes sense. Create image indexed. Create image RGB. Well, what format we're going to be using though? Well, let me check out real quick the capability, the caps viewer. 1 second. If I go to formats, what are the formats that are available to me? Optimal. I don't know. All right, well, BGRA 8. Maybe let's go with BGRA, or maybe we could, I don't know. Anyway, let's just try to do something here. So const image is equal to try image.create. Well, zig emg.image.create, and then here you give it an allocator. Then the width, well, let's say, I don't know, 720, and the pixel format. What's that? let's see, zig emg maybe dot pixel format dot, it's an enum, okay, and its index is just grayscale, is RGBA. So there's BGRA 32. I'm not sure what's the best format to work with in compute, honestly. Let's see, probably BGRA 8, but who knows. So best compute, I don't think there's a best, but I'm just gonna see, I'm gonna research a bit here. Best compute image format, best Vulkan compute. Where's the best for handling format qualifiers from compute shader? Oh yeah. So what format it's using here? It's using RGBA8 sRGB, seems like. Alright, so let's just work with that one then, fine. Let's check out some other sources maybe then. Yeah, seems like RGBA8 is the pretty much the norm, I guess, so far. Let's look for format maybe. No, there's nothing like that, I guess. Yeah, I think I'll just go with RGBA8. Open images. Yeah, look at that. Most of them very much just uses R8, G8, B8, A8, sRGB. Let's go with that anyway. At least most tutorials do. So I don't know if it does matter anyway, but okay, who cares anyway. So BGR RGB A. So there's 32 and there's 64. I would guess 32 that we need here. And yeah, so what's going on here? Okay, there's a lot going on here. I guess we could write to file. Oh, by the way, did we init that thing or what? Create. Okay, but so we have to d'init at some point, right? Okay, never mind. So d'init, it would be the fur. Let's make sure to d'init, I guess, and let's say image dot maybe save. No, write. So there's write to file path, and write to memory. Let's try write to file path, and let's just say maybe this is some image dot. Well, what encoder? I guess I would use QOI format. Encoder options. Let's see where those the encoder options are. And anyways, encoder. Well, let's see. QIA mid. Okay. let's look for C or what encoder options I'm supposed to give it. Right? There's no right here. So, well, I don't know where the stuff there. Okay, what this gives me? This gives me self. And self is this guy. Okay, where's the options here? So encoder. Okay, cool. Now let me see that. Image encoder options. All right, let's go. What's that? That's a union import slash emg. What the union? Oh, BMP void. So it's a union. You basically kind of give it the format. And that's a tag, I think, right? But I never really used the tagged unions, honestly. So let's have a look into the documentation real quick. There you go. Okay. Type tag. QOI. Maybe something like this. Variant. Honestly, no idea. Let's just see what's gonna happen here. So expected type src the formats QI, whatever that is. Node struct declared here. So maybe I have to actually use let's see, maybe image dot QI. How do you actually what the oh what is that even? No idea how you would use that, honestly. Helpers.zig. Union declared here. I guess maybe you actually have to give it a struct there. Error is ignored. Try. This should be var. Seems to work. Let's see. there's a QOI test file. Nice. But yeah, there we go. We got an image.qoi. But let me see how I can open it. Is there an extension for it or something? Because it doesn't seem like it natively. Okay. Alright, so this is what we got. Nice. So it works. Cool. Is this like... I wonder what data you have right now. Is this like just zeros or... I don't know. Let's try -d optimize real quick just to see something. Yeah, that's what I think. Maybe that the case. So we have a problem here. Well, zig out /bin /vulkan zig compute. Segmentation fault. Let's go. So this is the time to debug. Okay. I mean, I know there's probably because it's not initialized, right? But let's see. Create a lunch.json ldb. I mean, I had to actually set up debugging anyways. It's pretty simple to do so. Zig dash out /bin /vulkan zig compute, and let's go. All right, so let's try this out. An exception has occurred there. Oh, what the? Oh, actually, maybe it's not really. Are you kidding me? Is it the Vulkan stuff? If so, that's going to be crazy. It's talking about Wiki create share module. Let me just verify this. Hold on a second. Maybe it's not the image stuff. Hopefully, let's see what's gonna happen here. So var image. Is it really the Vulkan? Doesn't seem like so. Somehow it's telling me that the problem is in Vulkan stuff, but in fact it doesn't really seem like it. But again, it's talking about device wrapper, shader module init for some reason, main, weird. But let's try to initialize that image though and see if it's the real problem. Defer image.dinit. I don't know how you would do that though. Let's see. From file, from memory. Okay, you could give it a buffer. There's also an init function. Well, let's try to write. So write, actually read or what? Dot Lloyd? No. Dot from. Okay. From. Well, let's say from memory maybe. I'll just construct maybe some buffer real quick. No, let me see other stuff. Okay, so this create gives us self, which is this guy, okay? So, but where is the actual thing? So, where are the fields? Okay, there you go. Width and pixels. Inside pixels, there's a pixel storage. Interesting. And here we have RGBA32, so we have to look up for that one. It's a union. The RGBA32, which is this guy. Oh, there you go, Vulkan. Let's go. Nice. Nice that they put that stuff. Cool. Unorm. Alright. Well, we got something at least there. RGBA color. It's U8. So it's a struct with red, green, blue and stuff. But honestly, let's just try to maybe load some image. I don't know honestly what to do right now. Let's see. Defer image.dinit. Write file. Image.pixels.rgba32. So we have the PTR and we have the length. So can we fill this guy with something? No. Is there some function to fill the buffer with something? Memset. Oh yeah. Well, let's see memset and how that works. Sets elements. Mutable slice or mutable pointer to an array. Alright, cool. So maybe I could take this here and then element, I don't know, this would be an RGBA32 seems like, so but a slice, or is it what exactly? RGBA32, it's a slice of RGBA32s. So the element is RGBA32, right? So okay, EMG zig or zig EMG, the RGBA or what? Where I can find that? Maybe pixel formats? No. Dot what the? Okay, let me find out where I found that thing. It's inside color. So okay, RGBA32. And init RGB. Or I could basically say from this stuff. Okay, let's try to init RGB. What is this red T stuff? No idea. Oh, RGBA. So I guess it's gonna to be U8 maybe. So let's see. Let's try to say 0, green 0, and blue 0. Let's see how that would go. Zig build run. Let's see what we got there. Okay, we got a black image, seems like. So now would it still? Okay, hold on. Release fast. Okay, I'm glad it doesn't really seem like the bug is in the Vulkan code. Okay, so not the bug, but I mean the memory leak or whatever that is. The core dump stuff. Anyway, so this is how it is. Okay, init. Might use color.rgb A32. Init RGB. What about the parameters? Might use color.rgb A32. I don't think. I mean, what about the parameters? Yeah, already found it. So let's try maybe our red 255. So let's go to release fast and let's see what's gonna happen there. And nothing. Why it's still black? What? RGBA 32 init RGB. What about 255 in all of them? I did run it. Oh yeah, that's true. Zig build run. Good catch, man. Zig build run. I used release. Oh, release doesn't work. Oh man, maybe core dump is still there. Let's just try normal build. Okay, seems to work out. Nice. So I guess we could say 0 in the green, 0 in the blue. Zig build run. Let's see if it's red. Okay, works. Nice. Now, why it doesn't work in release build though? Dash D optimize equal release fast. And when we debug this, all right, something wrong with the shader module stuff. Okay, so I'm going to come back in a second. Hold on. Just gonna take a little break and I'll be back. Alright, back. Okay, Travis, goodbye. Have a great day. So, well, it seems like we have some sig fault. Oh my god. Well, let's see. Device wrapper. In vk create shader module for some reason. The device, I don't think that's the problem. Create info, probably not. Allocator, probably not. Shader module, I think so. There is some problem with shader module. It's in fact undefined for some reason. Oh yeah, it's actually supposed to be undefined. But what's going on here? Okay. Right, create info. So what's going on with this guy? Let's see the create info. Code size is good. P-code. There you go. So yeah, it's right there. The code is right there. So what's the problem then? That's very weird. P-code. PTR cast, this type align cast, code.ptr. Minimal shader. Where's the shaders stuff? Shaders. Okay, hold on a second. What about this? What would happen then? What if I do this? Okay, let's try now optimize. Still the sig fault. Weird. Right. And that's another level. AK create shader module. Address access protected default address 0xCA6900. Oh man. P create info. Create shader. Well, what could go wrong here? Could it be that we don't have a C there, maybe? Who knows? Still same problem. Destination type is constitutory to a line cast for code.pointer. Code size is right. Maybe I'm de-initting it somehow. Hold on. Let's go back to the code real quick. Let's see where we're creating the shader module. So the init device, then shaders dot minimal shader, and defer shader module dot de-inits. So what's the problem then? Can I do this? Hold on a second. API dump. Let's try to run it. Okay. So the last thing was Viki get device queue. Does that mean? API dump instance. Address access protected. Well, weird. I'll have to actually just check it out myself later on. So I think at this point I'm just going to stop the stream for now. So yeah, although I'd like to actually stage some changes. I'd like to add that module. So let's add it up. Well, how we're gonna do that? Well, stash or what? No. So these are already set. Okay, nice. Build.zig. Let's add that. Images.qoi. Nope. Discard for now. Lineage.json. Add main.zig. For main.zig, well, for now we're just going to comment this out. Okay, I'm gonna add those. add zig emg and commit sync changes. Okay, and I'd have to check out what's the problem with that thing. Okay, so that was it for this video, and see you later guys. Goodbye.